Precise.
I will begin with a word of prayer.
I don't know. I'll take that.
Dear Father, we thank you for this day. Again, I thank you for this class, and just ask you to this day help us to glorify you. You know, I pray, Lord Jesus. Amen. All right. So again, my apologies about the delay here. I need to talk to you guys about the method of annihilators. So let's do that. And so to appreciate this method, I think you first need to work some sort of backwards examples. All right? And so here's like my first backwards example. Y equals to, let's say, cosine of x. All right? Here's the question. Find the lowest order differential equation, constant coefficients, which has this as a solution. Can you guys tell me what it is? What's the lowest order differential equation, constant coefficient, which takes that as a solution? How about this? This is a solution of what?
Y double prime plus y, 0.
Y prime prime plus y equals to 0, right? In other words, if we look at the operator, d squared plus 1, right? It will kill, it will annihilate cosine. This makes d squared plus 1 an annihilator for cosine. Okay. Let's try another example. What if I'm up against, y equals to, oh, I don't know, e to the 3x plus x squared. What could this appear as a solution for? What differential equation would take this as a solution? Let's write it in operator notation, right? We can get that e to the 3x. If we put a d minus 3 in our differential equation, that will pick that up as a solution, right? How do we get x squared? What's that coming from? How about d cubed, right? The third derivative of x squared is 0, is it not? And so there you go. That, when we feed it e to the 3x plus x squared, we get 0. So what we're doing right now is we're working backwards. I showed you last week how to find solutions for a given operator, finding how to make it 0, right? Now I'm asking the inverse question. Here's a potential solution. What's the smallest operator that makes that sends that thing to 0? Another example. What if I'm up against y is equal to, say, oh, I don't know, x squared e to the minus 2x cosine of 3x. How on earth would you send that monstrosity to 0? What's it coming from? See, we need to work backwards, is the idea. What is that? That's signature of a characteristic value, what? Lambda equal to? What, minus 2? Plus or minus what? 3i, right? That's the kind of characteristic value which gives you those kinds of exponentials times that kind of cosine or sine, right? All right. I mean, okay, so, but how many times would that have to be repeated? Like once? Well, one repeat, like if it was a double value, you'd get x times cosines and exponentials, right? There's an x squared there, so this has to be repeated. There you go. Technical term. Not widely known, but there you go. So it's a triple root. Now, in terms of operators, we're looking at d plus 2 quantity squared plus 9. That alone picks up e to the minus 2x and cosine 3x as solutions, right? That will send those functions to 0. But because we need a 3p, we got to take this thing, we got to cube it. And if you feed that x squared e to the minus 2x cosine 3x, guess what you'll get? You'll get 0, working backwards. Example 4. If I had y is equal to like, e to the minus 2x sine 3x plus x e to the minus 2x cosine 3x plus x squared e to the minus 2x sine 3x. Right? Suppose I was up against that. I want to find the annihilator for this function. I want to find an operator of lowest order which sends this function to 0. What should I do? Well, the answer is just call the thing we had right before A for annihilator. And it's true that A acting on this y, it's still 0, all right? Like, those functions all fit under the solution set of that triple, like what are the solutions? What is the solution to this right here? Like, let's write them out, let's be explicit. Like that's a 6th order differential equation. If I put that equal to 0, right? This is a 6th order ODE. What are the solutions? The real solutions are e to the minus 2x cosine 3x, e to the minus 2x sine 3x, x e to the minus 2x cosine 3x, x e to the minus 2x sine 3x, x squared e to the minus 2x cosine 3x, x squared e to the minus 2x sine 3x. All right, all of this. These are all sent to 0 by my annihilator there. And therefore, because it's a linear operator, if I take any linear combination of those, it likewise sends them to 0. Are you guys starting to see what I'm doing? This is a kind of harder example. So let's make a table. We're going to put, we'll put the annihilator we want, and we'll put G such that A acting on G is equal to 0. So our goal in constructing this table is just to make a kind of list of examples. In the left-hand side, we're going to put the differential operator of like lowest degree, which picks up the function as a, it'll start out with simple 1. What should I make my annihilator for 1? Just D? Yeah. How about e to the AT? D minus A, all right. How about cosine of, say, dt? That we would do d squared plus b squared. That would kill that. Because that's coming from lambda equal to plus or minus IB, right? And that's the solution of lambda squared plus b squared equals to 0, if you like. Really just working the results last week backwards. Let's see here. So if I had, e to the, say, alpha t cosine beta t, we know what to do there, right? We've got d minus alpha quantity squared plus beta squared. That's like we wrote from last week essentially, but now we're just looking at it in a different way. Okay, so if I have, t to the power n, I just do, d to the n plus 1, all right? That'll kill that up. Let's see here, what else? If I have, t to the power n times e to the a, t, what do I do? I do like d minus a to the what power? N is almost n plus 1. N plus 1. See, you can see this example up here as the n equals 0 case for that guy. Right? Yeah. And then we can mix and match, right? Like, so if you have, for instance, 1 plus e to the at, then you do d times d minus a, right? If you have, e to the at plus, say, t to the n, then you do d minus a times d to the n plus 1, right? Let me throw something new into the mix here. How about cosh, hyperbolic cosine of beta t?
Would it be just like cosine in a sense, where it's d squared plus beta squared? Oh wait, you added stuff to it.
But, oh, no, I'm not adding stuff to it. I'm just telling you, you guys may or may not know. You should know that hyperbolic cosine is the sum of exponentials, right?
Yeah.
So, in light of that, it should be clear that we do d minus beta times d plus beta, right? Which is actually d squared minus beta squared, yeah. The same thing will kill sinh of beta t. So sinh and cosh are just like sine and cosine, just to change a plus to a minus, or vice versa, depending on how you look at it. All right, so anyway, the theorem that I point out here is simply this, is we're given G, which is product, sum, etc., of solutions to constant coefficient ODE, we can find an annihilator A for which A acting on G is equal to 0, and ultimately A is some polynomial in the differentiation operator, right? It's some polynomial in the differentiation operator. All of my annihilators have been polynomials in the differentiation operator. So here's a thought experiment for you guys. We're trying to solve the non-homogeneous problem, right? Our goal, our mission, should you choose to accept it, is to solve L of y equals to G, where L is equal to some polynomial, let's say f, in the differentiation operator. Both these guys, polynomials. That's just a fancy way of saying we're trying to solve the constant coefficient differential equation. All right? So check this out. This inhomogeneous term G, if I can annihilate it, what I can do is I can take this differential equation right here, you see? And if I annihilate this with the annihilator for G, I've got AL acting on Y is equal to AG. All right? Well, what is AG? Well, by construction, that's 0, right? That's 0 by construction, assumption. And what is this? Well, this is nothing more. If you write it back in my polynomial notation, you got like your P of D times your F of D acting on Y, right? But what this is This is a constant coefficient ODE. And by the way, we completely know how to solve all of those, which means that we can solve that equation I just wrote down. And the beautiful thing is that by solving that differential equation, you can read from that the form of the particular solution for your original problem. This gives us a way of improving on the naive solution I showed you last time and actually finding like the straight up the right form for the solution. So like let me show you how this works for a specific example. Sorry I didn't give you guys a quiz today. I know you wanted one. Don't worry, I did write one up, I just didn't print it out, so, you know. I guess it could have happened. Maybe next time. So like some of this stuff makes decent in-class quiz questions, like choosing annihilators for a given function, like given the right-hand side of this table, fill out the left-hand side. Perfectly legitimate 5-minute quiz, right? But working out the details of what I'm about to do, not a 5-minute quiz, like a 20-minute algebra exercise, right? So that's kind of less fun aiming for in class because we only have so much time, as you know. So okay, so the problem I want to solve, I'm at example 5.
Correct.
How about this? We want to solve y prime prime plus y prime equals to, let's say, e to the x plus x. Also, we want to find the general solution to this problem. So just to recap, what we're looking for, two things. One is the homogeneous solution, right? And that we can write down simply from the characteristic equation. And then the other thing we're trying to find is the particular solution. That's the thing we haven't quite sorted out yet. Yeah. The homogeneous solution. And like the theorem, just to recap here, remember the theorem says, like there's a theorem, y is equal to yh plus yp, where yh is equal to c1 y1 plus c2 y2. And in this case, like y sub j prime prime plus y sub j prime is equal to 0. That's the homogeneous problem. So like we can figure out the homogeneous solution very simply by using the stuff we talked about last week, right? We write down the characteristic equation if you like. So my characteristic equation, lambda squared plus lambda, which is equal to lambda times lambda plus 1. I set that equal to 0. Aha. Lambda is either equal to 0 or minus 1. My homogeneous solution has the form c1 e to the 0, which is just 1, plus c2 e to the minus x. So there you go. That's the form of my homogeneous solution. Right? Now, at first glance, you might look at the inhomogeneous term here, right? The inhomogeneous term, which is this. This is my g in the language of the algorithm. It doesn't, at first glance, appear there's any overlap, right? Because I've got an e to the x, not an e to the minus x. Those are linearly independent, right? We calculated the Wronskian last time, and we saw that that's the case. And x, well, there's no x there, right? But what's the problem? Where does x come from? X comes from lambda equals to 0, doesn't it? X comes from lambda equal to 0 repeated. That's how we get x in the homogeneous solution set. So for that reason, if we were to try to do the naive thing, it wouldn't work here. By the way, the naive guess I keep talking about, the naive guess for this would just be like, you just do a e to the x plus like dx plus c. That would be the naive guess, and this will fail. All right? Okay, so the method of annihilators, let's demonstrate the method of annihilators. So we're going to use the method of annihilators to find correct form for the particular solution. All right, so what's my annihilator here? How about this? I'm going to do A is d minus 1 times d squared kills e to the x and x, right? My d minus 1 will kill off the e to the x, and my d squared will kill off the x, right? My original problem, right? This right here, I can rewrite as d squared plus d acting on y is equal to, e to the x plus x, right? So what we do is we take the differential equation and we annihilate both sides. See, this says that d minus 1 times d squared. And if you don't mind, I'm going to factor this. What has this factor? This factors, right? D times d plus 1, right? So I'm annihilating both sides. D minus 1 times d squared. And then the original differential equation, which was d times d plus 1, acting on y, is equal to my annihilator, d minus 1 d squared, acting on my homogeneous term, which here is e to the x plus x. Now by construction, the right-hand side is 0. Right? The right-hand side is 0. See? That's 0. But then we can combine things, you see. So this is actually like d minus 1, d squared times d is d cubed, and d plus 1 acting on y equals to 0. But we developed a series of lemmas last week that showed us how to write down the answer for this. What's the answer? Well, the general solution to this homogeneous problem has the form y is equal to like c1 e to the x plus c2 plus c3x plus c4x squared plus c5 e to the minus x, you see. That's the general solution to that homogeneous problem. Now here's the genius of the annihilator method, is to go, oh, okay, so whatever's here is not the homogeneous solution. That is what I should use for my particular solution. All right. So you look at this. What's the homogeneous solution? You see we have it up here, right? See this? Here's my homogeneous solution. And so looking down here, this piece, right, and also this piece. So these two guys, these are just the homogeneous solution. We don't care about that. We know that we cannot fix the values of C1 and C2 in the sense up there or down here in the sense C2 and C5. We can't figure out the values of those coefficients without initial conditions. So like those are part of the solution. It's unavoidable. But the rest of it, you see, the rest of it is the particular solution. So like this guy, and this guy, my particular solution is going to have to form a e to the x plus dx plus cx squared. So this right here is the form of the particular solution. So sometimes I ask for you guys to set up the particular solution, but not to determine the coefficients. If I ask that question, I'm asking you to go through the steps I just went through and stop there, right? Now to find the actual solution, we need to plug that back into the differential equation and work out the algebra to find the values for A, B, and C, which is what I'll do next. But yeah.
Okay, just so I'm clear, you factored out the operators on the one side, and then you applied operators to both sides to get rid of.
Well, I think I need to factor the operator in order to appreciate how they're intertwined. You know, like factoring this d out was instrumental to making the d cubed over here.
I just mean you factor it out of the left side, right? You started with y
Yeah.
prime prime plus y prime, so you factored out the operators out of that.
Yes.
So you could apply just y, and then you applied operators to both sides
Right.
to get rid of the,
Right, but yeah, absolutely, but the thing I applied to both sides,
yeah,
it has nothing to do whatsoever
Right.
with the left-hand side.
right.
It has absolutely everything to do with what's here. So these are separate worlds, but they are, in as much as they're interlinked, we depart from the naive solution. You notice the naive solution is almost right. Like part of it works. A to the x piece is fine because there's no overlap there, but this bx plus c actually has to be multiplied by x to be the correct form. And like, maybe you don't believe me. I mean, you don't have to believe me, but I am telling you the truth. But let's see here. Let's work it out. So again, sometimes on the test or quiz or whatever, I don't want it to make you go past here. I'm just like, okay, that's the correct template for the particular solution, right? It's the correct form of it. But if we actually want to find the general solution, of, in this case, y prime prime plus y prime equal to, e to the x plus x, then I have to go further. I actually have to plug in my particular solution and work out the algebra and see where it takes me. So let's see if we can do that. All right, so we need to differentiate this thing. What we got? I usually try to write again my y prime. Oh, by the way, did you notice that I did not keep using like C1, C3, and C4 because why? The reason's not terribly deep. It's just I don't want to keep writing C1, C2, and C1, C3, and C4. Right? I'd rather write ABC, you know? And you might be like, well, aren't you worried you're going to confuse the A here with the annihilators we were talking about a minute ago? And the answer is, no, I'm not going to get confused about that. If you're getting confused about that, oh, I guess you're very confused. But don't do that. This is, if you want to, you can go back here and make it all like that or something. Make it all artsy. And then you won't be confused between that A and this A. This is undetermined coefficient, right? The undetermined coefficients here are A, B, and C. Now that's kind of it's an unfortunate language in some sense, because we definitely don't mean to leave them undetermined in the answer. They're going to be determined by the differential equation, unlike the constants in the homogeneous solution, right? Okay, so here we go. Yp prime is a e to the x plus bx, well, plus b plus 2cx, and yp prime prime is a e to the x plus 2c. Thus, yp prime prime plus yp prime is apparently a e to the x plus 2c plus a e to the x plus b plus 2cx. Now that's all equal to the inhomogeneous term, which here was e to the x plus x. So how do we solve this? Like, how do you figure out A, B, and C? What do you do?
Combine like terms and just the coefficients in the right, and then
Okay, so you're like combined like terms. So yeah, sure. You think we got 2a e to the x. All right. Hold on, I tried. We got 2a thank you for these. Let's see here, 2c plus b, and then we got ourselves a 2c times x is equal to 1 times e to the x plus 0 times 1 plus 1 times x. There, I'm writing the 1 and the 0 to just be kind of dumb to point out what's going on here. The larger point here is that e to the x, x, and 1 are linearly independent functions. And one of the major theorems that we learn in linear algebra about linear independent functions is that you can equate their coefficients because they're independent. So the only way that this equation can be true is if separately 2a is equal to 1, if 2c plus b is equal to 0, and if 2c is equal to 1. Equating coefficients like of e to the x, 1 and x. So I have 2a is equal to 1, I have 2c plus b is equal to 0, and I have 2c is equal to 1. So therefore a is a half, c is a half, and b is -1, thank you. So put it all together, final solution, what do we got? So going back to the theory, we have the homogeneous piece, which is c1y1. So I go like c1 plus c2 e to the minus x, that's my homogeneous solution, all right? And then plus 1 half e to the x, minus x,
Plus 1 half.
plus 1 half, thank you, I've lost track of what's what. Is that right?
So 1 half x squared.
1 half x squared. Yeah, yeah. Oh, yes, thank you. Very good. And there you go. That is the general solution to the differential equation. And that's the method of annihilators. The method of annihilators allows us to see what the correct form of the particular solution should be. All right. But it doesn't actually find the particular solution. It always comes back to algebra at the end of it, you know. A very popular mistake on the next test is to go through the trouble of constructing the correct form of the particular solution and just stop there and not do this. So you get like half credit because you didn't finish the problem. Don't do that. Since I'm telling you this now, it won't happen, right? I'd love for you to tell you that that's the truth, but the thing is I've had this conversation with differential equations before, and they also forgot to do it. So I know that, and maybe right now this conversation we're having is causing you to have that mistake on the next test, if so, I'm sorry, but you know, you can't escape this self-fulfilling prophecy, I guess. Anyway, so like, we can't do better than this without initial conditions, right? If you take this problem, and then we add furthermore, also, y of 0 is equal to 0, and y prime of 0 is 1. If we have these initial conditions, then we can take our general solution and choose values for C1 and C2 which make it so, right? But you notice then, like, okay, so we have like, you know, 0 is equal to C1 plus 1 half. So therefore C1 is minus a half. And then what's y prime? Right, if I differentiate, I get that. And then so like y prime of 0 would be minus C2 plus a half plus 1 equals to 1, which would tell me that C2 is, if I haven't made a mistake, C2 is a half. And so I would then find the solution minus 1 half plus 1 half e to the minus x plus 1 half e to 3x minus x plus 1/2 x squared. And that would be the solution to the initial value problem that I just wrote on the board. Now, I don't usually do that because I think it's, you know, I can learn most of what I need to about what you know, even if I don't tack on initial conditions to the problem, right? But the point should be made that to solve the initial value problem, you do have to use the general solution. It wouldn't make sense to fit the initial conditions just to the homogeneous piece, even though that would be easier. It would just be wrong. Because the actual solution is the homogeneous plus the particular. That's the one that actually solves the differential equation, and that's the one that you have to fit the initial conditions to.
I don't think that works.
Oh no, what did I do?
I think we need, so,
I'm wrong here.
maybe,
Where?
so C2 e to the negative 0 would just be negative C2, so I don't know if you get rid of, like, I don't think it's like just C1. If you plug in 0, you can see it wouldn't, I don't think it would work. Got negative 1 plus 1/2 plus 1/2.
It doesn't feel, so where did I make my mistake? Did I differentiate it wrong?
I think 0 equals C1 plus 1/2, I don't know if that's true. I think it's C plus 1/2 plus C2, or minus C2. I don't know.
Oh, yeah. Thank you. So right here, you're like, that's supposed to
Yeah,
be.
well, the 1/2 is there as well.
Yeah, but C1 plus C2,
Yeah.
plus, like you said, plus a half. Yeah. They're not so fast here, huh? They're not so fast. I got that equation. And, but this one is okay.
Probably,
Oh, so usually you get two equations, two unknowns for these. But this one's kinder, because when we differentiate, the constant term goes away. So the second equation is just for
Is-
C2,
okay.
glucon is half. And so when we put that up in here,
You got negative 1.
yeah, C1 is -1. So C1 is negative, so we put a -1 here. And then I think there'll be a piece with the solution,
Yes.
because once we put that -1 there, when we plug in x
Yeah.
equal to 0, we get -1 plus 1, which is 0 like we want. Very good. So what secret technique did the president use just now? Is this some sort of like
Algebra.
some sort of chess, some sort of, what do you call that when you have the thing that you're doing in the chess to start with? It's called
The opening,
the opening, yes. What opening did he use on my solution?
Sicilian defense.
The Sicilian defense? So, I mean, he assumed that I was wrong, which is helpful. And, he assumed the possibility that I was wrong. Put yourself in my shoes, assume you could be wrong, right? And if you think that way, you should check if it actually works, right? Which is when you plug in 0 and say, hey, wait a minute, 0 is supposed to go to 0, and it didn't, which means I made a mistake, which I did. Thank you. I very much appreciate these kinds of comments. So. All right, so this is the method of annihilators, and we could do more of these. But I want to show you guys the other technique, all right? The other technique is variation of parameters. And so I will show that to you, and I will do that thing we do with the hat. I think I have something to turn back to guys too, lest I forget, because our beloved creator has created things, and so you'd like to have them back, right? So if I can do two things at once, that's very debatable. So listen, this method we're currently using is only good in as much as the inhomogeneous term just happens to line up with one of these solutions to the homogeneous problem, right? Now that's not super limiting, because after all, what's the solution to the homogeneous problem? Well, like tons of stuff, right? Like exponentials, sines, cosines, polynomials, all that stuff, the products thereof, sums thereof are solutions to the homogeneous problem, which is super awesome. But not everything's like that, right? So let me show you the other side of the tracks, so to speak. We'll do more examples of this, but I think it's good for you to see an example, see the idea, let it sit, and then come back to it. So since the other thing that we need to talk about is various parameters, numerical, can find my, oh man. Where's my laser? You know what would be annoying is if I found my microphone. I can hear now, right? That would be funny, wouldn't it? But nope, didn't happen. All right, so variation of parameters is the other way of doing things. And so I'm going to go through this general derivation with you right quick. And I'll spare you me writing it out. You're welcome. So basically the idea is just this. If we're solving a nth order problem, suppose you know the fundamental solution set is y1 through yn. This doesn't even have to be the constant coefficient problem, all right? So I'm just saying, suppose you know the fundamental solution set of Ly equals to f, has fundamental solutions y1 through yn, all right? They're a linearly independent set of functions that solve L of y equals to 0, right? The idea of the variation of parameters solution is to say, oh, well, then I can make up these parameters, v1 through vn, such that if I make these functions the right way, then this kind of like multiple of my fundamental solution set, well, that should work for my particular solution. This is just a guess, all right? And then so you make that guess, you differentiate it once, and that gets you to here because you got a product rule a bunch of times. And then you're like, oh, well, I don't like that. That's kind of ugly. And I'd like to get rid of some of these things. So you say, well, I'm going to assume that I can make a guess such that all these are 0. All right? You're like, well, why can you make that guess? Well, just hang with me. We can try, right? It's like I usually give the example of like you're trying to find a spouse. Maybe one of your conditions is, they have less than 5 piercings on their face, right? You probably can impose this condition at the moment. Sorry, I'm not offending anyone. There we go. Let's see here. So we can impose this condition. If it's too much, then we'll not be able to find a solution, right? So you impose that condition, and then you differentiate. Again, and it gives you this. But then you're like, well, it's still ugly. I'd like to get rid of these. So basically, at every step, we're getting rid of things that involve derivatives of the parameters. Take the third derivative. We'll get rid of the terms with the derivatives of the parameters. Assume that can be set equal to 0. And so forth and so on. And so forth and so on. Eventually, you get to the n-1th derivative. And then what you do, much like our derivation the other day of Abel's formula, we plug in the differential equation at the like y prime prime, or there. So like here we're plugging in the differential equation for the nth derivative, replacing all these terms, which gives us the nth derivatives, all this business. All right, great. And then, putting this all together, this is what happens when you plug it into the differential equation. You get this, which then simplifies down, lovely, to this eventually, all right? And so then if you put this all together, again, my wish list of constraints, right, here and here and here and here, right? So like the first n-1 rows of this, those are just my ad hoc constraints to eliminate additional conditions on the derivatives of the parameters. The last one is actually the differential equation itself plugged into the solution. As you can see, the presence of the inhomogeneous term divided by the leading coefficient. But then the thing is, this is the matrix whose determinant is what? Remember what we call the determinant when we take functions in the first row, derivatives in the second row, all the way down? That's the Wronskian of my fundamental solution set, which I know is invertible, because I'm assuming in linear independence of the solution set. And what that means then is that the inverse matrix exists, and I can solve for this matrix of derivatives, and therefore I can integrate both sides and find formulas for my parameters in terms of integration. If you guys know Kramer's rule. Remember Kramer's rule from circuits? Some of you? So like here's a Well, that's an example of Cramer's rule, but anyway, so we have stone cold formulas for, you just calculate the sub-Wronskian, divide by the Wronskian, integrate that thing times the homogeneous term, that gives you the first parameter and so forth. Now, there was one semester of differential equations where I actually tested this at third order, and forever hereafter I never test it. Because it's horrible. It's truly horrible. But the good news is, at the n equals 2 level, and perhaps we should just derive this from scratch. For just n equals 2 case, that probably would be good for us, but if we don't do that this semester, I won't cry. But for the second order case, when you go through the formulas I just developed, what it works out to, the Wronskian is just this difference, all right? And when you calculate those determinants of the sub-Wronskian, it just works out to this and that, which gives me the following formulas. V1 is this, and V2 is that. So if I want to calculate the particular solution, I simply have to do this integral, that integral, and multiply them by my y1 and y2. Lo and behold, general solution. So like that. Here, I'll show you an example. To solve y prime prime plus y equal to secant x, first of all, I cannot use undetermined coefficients. Secant is not a solution to a homogeneous problem, right? It's not there. Search your heart. It's true. But the homogeneous solutions are cosine and sine. So the Wronskian here is particularly nice. It's 1. So when I calculate V1, I just have integral of secant sine, which is log cosine with a minus up front, or if you like, log secant. V2, on the other hand, is the integral of secant cosine, an integral I very much enjoy doing. Actually, this is a fun integral to ask in calculus too, for partly wrong reasons. It shouldn't give me joy to see students not be able to do this, but somehow it does. But it shouldn't give me joy. I should feel sadness for them when this doesn't go well. But hey, let's face it, if you're integrating secant squared and you don't know that there's nothing to do, you're in a bad spot, right? Because it's tangent, right? But how do you know that? You just know calculus, right? But anyway, so this integrates to x. Lo and behold, my V1 is this, and my V2 is that, and you put it together, solution. That's the general solution. So various parameters, totally general, but comes at a cost, integration. All right, so anyway. We will do more of both of these in the days to follow. Thanks, guys. Sorry again for the lackluster quality of the audio this lecture.